and then
Thank
and
you.
always
Thank you, Dr. Liu. So with that, hello everyone. I am Rahul Chakraborty from Dominion Energy, Virginia. Today, my colleague Andrea and I are going to present on the topic IBR readiness evaluation from interconnection studies to energization phase. Now, there are a few words in this title which needs further explanation before we move on to the following slides. By readiness evaluation, we mean the conformity tests of the IBR for different standard requirements from planning phase to an operation phase. Interconnection study mainly refers to the planning level analysis where detailed studies are performed from both steady state and dynamic perspective. Once those electrical viability of the interconnection is judged and the required system upgrades are approved by regulatory bodies, then the project construction happens and finally energization of the site. So through this presentation, we will try to give an end-to-end picture of IBR integration from utility perspective in relevance to the scope of work in UNIFI. Now, with that introduction, let's briefly mention the contents of this presentation. First, we will introduce who we represent here, the company Dominion Energy Virginia, and then to be specific, the electric transmission division where I work in the transmission planning. We will show where we are geographically, who are the relevant regulatory bodies, the different differentiation between system planning and operations, who are the main drivers when it comes to expanding or developing our system for future needs, the practical challenges of generation interconnection process, how to ensure the future grid forming solutions are implementable when different entities are involved from ownership investment perspective, when it comes to this type of IVR integration. Then we will discuss some of the key operational challenges that we have dealt with in the current IBR dominated areas we have. And at the end, we will mention some of the external collaborations that we have. Now, so this slide shows why, as an utility, Dominion is not a monopoly. There are many key regulatory bodies which keeps utilities like us in check so that we operate with the best interest of our customers who are the ratepayers. There are bodies like Federal Energy Regulatory Commission, North American Electric Reliability Corporation. Then there is PJM, who is our regional transmission operator, and then the state corporation, local authorities. Each of them play different role when it comes to like evaluating our engineering solution, seeing that is it economic enough, and then kind of giving the decision on approving those solutions. NARC is the body which is the main driver of proposing different changes which are going to, enforce the reliability standard more and more as we go in the future. And then PJM, even though in the slide I mentioned regional transmission organization, they play both as a planner as well as operator in our system, in transmission. And then whenever we propose different projects, even if PGM approves the electrical solution, it has to be approved by the state commission, from in general like state of Virginia's point of view, how the project is looking like. So these are the key regulatory bodies, and here in US we are in the eastern side of US in PJM. There are many utilities, but Dominion has the highest load growth. I will come to that in the coming slide, why it is like that. And that is one of the main driver for our expansion. And by PJM, it is Pennsylvania, New Jersey, Maryland interconnection. And they host one of the biggest load in the entire country. Now, in our territory, Dominion's goal is to meet the Virginia Clean Economy Act. And I mentioned this word, greenification. So, why is that? Because we always talk about the digitization and then all this big data that's coming out from the power system and how it is going to help us to do better control optimization. So all this digitization, datafication, everything is leading up to meeting the goal of the net zero, which is like the green economy. So that's why this word I mentioned, greenification, and our target is we want to have 16,100 megawatt of solar by 2035. There is target of 5,200 megawatt of wind, offshore wind in 2035, and similarly for energy storage. And also we are trying to improve the way we serve our customers with better monitoring, so that different optimization algorithm can be applied to reduce down the network losses and make the network more energy efficient. So these type of targets are there, and in coming slide we will show how we are working towards these targets. The force of driving this infrastructure need, mainly you can see in the slide, there is economic growth, there is of course aging grid assets which need to be replaced, and also there are like NERC criteria. So like I mentioned, NERC is the body which has different type of compliances, and as a utility we want to make sure that we meet those requirements. That's why for meeting those requirements, we propose different projects, and that is also a driver. But the main driver you can see on the right is the data center growth. Now, in our zone, there's a huge increase in the number of data centers lately, and we are continuously receiving application of data center builders. Why is that? Because of the AI boom, as we all know that when companies like Microsoft, Amazon, Meta, they build their big data centers, someone in the back supplying power to those data centers. And one of the utility which is hosting the largest concentration of data center in Northern Virginia is generation and stuff. So these are the main drivers. Now, um, when it comes to seeing that okay, how these drivers are going to change in future, we see that there are huge deviations that are coming in the forecast. So think about this gray line, which say is showing a forecast from 2021, say 6 years down the lane, how the
Rahul,
system is going to look like.
Hello, Rahul. It seems like your slides is missing. Could you reshare the screen? It seems
I
like
think
we
you dropped out for a second and it stopped sharing. So if you can share the slides again.
right.
Oh,
It's okay, perfect. Okay.
was I in this slide?
Yes, it's you are in the slides with the title Load Growth
Sure.
and Energy. Yeah.
Sure. So, in this slide, you can see that from the gray line, which is kind of showing from 2021, 2022, how the forecast would have been look like for 2027. Now, as we move forward, say in 2022, we see that, okay, what we thought it will be 6 years down the lane is actually more, 2.6 gigawatt more. And then when it comes to 2023, we realized, okay, what we thought 5 years ahead, how it will look like. Now in 4 years ahead, in the same year, 2027, the deviation is even more. It's 3.5 gigawatt more. So today, if from a planning department where we are dealing with future scenarios and we are, say, proposing new solution for 5 years down the lane, and then next year we see there's a huge forecast deviation, so we have to reevaluate our solution. So that's the reality we are facing. And why the planning department exists, because say when you are trying to expand your system, it takes time to build those infrastructure. So that's why every utility, they have a dedicated planning department which kind of work with the transmission operator RTOs to kind of propose the solution to different challenges like load growth or generation interconnection related challenges for futuristic scenarios. Now, let's see how we typically evaluate our planning solution given these huge changes in forecast that we are seeing every year. First, like what model to use for this kind of study. The US grid is mainly divided in three main interconnection: east, west, and Texas. For eastern interconnection, where we are in PJM, our system upgrade planning consists of mainly three cycles, like regional transmission expansion plan, where we study how to solve for the load growth for 5 years ahead scenario, given we have information on the future topology, which will be present after hosting generation for next 5 years. And then comes the generation interconnection, that the GI cycle, which is most relevant here for this as this process which dictates how the transmission level generation are going to be in the process of PJM's GI cycle. Unless PJM approves the application of a generation developer, certifying that the electrical solution makes sense, the developer most likely will not get approved by the local authorities to build or connect the sites. So in addition to that, there is another cycle, which is market efficiency open window, where we solve for the congestion in the system. So with all these different objectives, where we are solving for the system upgrade that is needed to host the new generation, to supply power the new load, the planning model, why I'm mentioning this is the scale of the model is like a 90,000 bus model with around 110,000 lines and around 30,000 generators. So typically in planning, when we do studies, they are positive sequence simulation. If we are doing dynamic study, they are not EMT. We do EMT for some specific purposes if we are doing some local studies, but as a whole, when we are doing say for eastern interconnection or PJM, we use the multi regional modeling working groups dynamic model, which is like a standard PSSC model. Now in generation interconnection cycle, this slide shows that what is the reality we are dealing with. You can see that there are many projects which are active in the queue. Compared to the 2010, the queue has increased significantly in 2023. Now, why is that? I will show it in the next slide. But you can see from this table that the maximum number of projects are in PJM footprint. And the active capacity in the queue is 2,600 gigawatt. So actually, if this all generation gets implemented, we are all good. Like we are achieving net zero by just this generation. But the reality is most of them will drop out. Why is that? I will come to those points in the coming slides as well. So in the like past 2000 to 2018, the trend we see that there are many developers who dropped out. Only 19% of the request or 14% of the capacity actually got to the commercial operation. And as we go from 2018 to 2023, the queue is increasing. So the developers who are applying to build generation sites in different utilities territory, most of them don't actually go to the energization phase. They don't even go past the interconnection study phase. So we need reforms for that. And PJM has come up with one of the reform strategy. Actually, MISO is also implementing something similar in the Midwest region. So what they have changed is that earlier the generation developers, when they used to apply, the RTO used to study their application like first come first serve basis. But now they have converted that to a cluster study process. So what that means is, say 10 generations are trying to build or saying that they will build generation sites in a particular zone. So instead of analyzing their effect individually, our current process is to kind of cluster them and see what is the cumulative effect. By cumulative effect, it can be there may be thermal overload in a line, there may be voltage over voltage issues, there may be short circuit current related issues. So we need to assess that, and if there is any system upgrade needed for hosting that generation, so that should be communicated with the developer and they have to pay the price. Now as it is a cluster, the price or the cost will be divided in among the developers who are in the same cluster. So here I show in this slide the three phases what PJM is currently following, like a transition from first come first serve to cluster study process. In the phase one, we kind of do the load flow analysis, then phase two the short circuit, phase three is the dynamic analysis. And with all these different analysis, the main goal is to filter out if there is some developers who are not serious about actually building the site, whereas to find out the generation which will actually go passing the interconnection study phase. So that's why there are different fines that have been imposed in these phases, like there's something called readiness deposit which the developers need to pay when they apply for building for actually initiating the study process. And that readiness deposit is 100% at risk once they pass the decision point one and they say that they want to stay in the queue for the study phase. So why I am saying all this, because to give the reality of the situation, no matter how we propose the engineering solution, there is someone who is going to pay for that solution so that it get implemented. And those solutions have ownership, multiple ownership, depending on if the entity who is building the site wants to have grid forming functionalities or not. I'll show that in the coming slide. But before that, here in this slide I show that in these three phases that I was mentioning for generation interconnection, we use different softwares. So the one contingency analysis is one of the very basic criteria from power system point of view. Like no matter how good the solution is for operations, we need to make sure that if we lose any component, still the system is stable and reliable. So that's why n minus one is the first criteria, and then some of the contingencies we do n minus one minus one. Then the generation deliverability and load deliverability are kind of like seeing different redispatched scenario of the system to see that, okay, if a utility can import or export enough amount of power to support each other or not. So we do that using this software called Tara, transmission adequacy and reliability assessment software, the kind of a standard in utility space. Then the fault current calculation is done in Aspen, and finally transient simulation stability mostly in PSEC, but sometimes we use PSCAT for some specific studies. Now coming to this ownership or implementability issue for GFM, I would like to mention that how a GFM technology implementation can depend on multiple parties. Like the cost sharing can be very vital. Even though like wind, right? Co-located with e-statcom, energy storage and statcom may act as grid forming resource, which is shown in this reference. But there can be different ownership involved to implement that. So a project developer, when they typically apply to build a site, it is typically at the interconnection point between transmission and the generation. So they are going to pay for this. And when they apply for the queue to PJM or the RTO, and the transmission owner, which for us say the Dominion is the transmission owner, they evaluate the solution and they say, okay, we want this resource to be grid forming. That's why we want to put a energy storage and statcom, and it is going to cost this many $1 million. Now the developer ideally should pay for this, but they may back out saying that, okay, we just want to be grid following, not grid forming. With the current policy, the situation is like that. So that's why when it comes to grid forming technology, we need to be sure that the solution we are proposing is implementable from the practical point of view. We always talk about technological solution. Here we need to think about techno economic solution. That is one of the point that I wanted to mention, that even though this solution can provide all different type of services, with the current policy, it is increasingly difficult to convince the project developer to pay for all the upgrade that is needed to connect their site as a grid forming resource. So that's why I would say that in our planning phase, PJM is kind of studying the scenario how the generation interconnection cycle will happen from this transition cycle to actually in future, how we are working with PJM to see that if there is any optimal GFM GFL combination that we can propose by working with our TOs to make our system better equipped with the devices that can handle the dynamics that we typically see from IBR. And I hand over to Andrea to show some of these operational challenges that we are already seeing from these IBRs. So Andrea, over to you.
Yeah, thank you, Rahul. So yeah, my name is Andrea Pinceti, and I work in our electric transmission strategic initiatives and special studies group. And so what we do as part of our work is we're looking at the impact that IBRs are already having on our system, and we try to perform advanced studies, simulations to try and tackle some of these challenges that we're seeing. And so, in my part of the talk today, I'll try to give some specific examples of the issues that we've already kind of started seeing on our system, stemming from a higher penetration of mostly solar PV on our system, and also explain some of the ways that we're trying to address them by developing new tools or new processes. So, next slide. So we already saw how, from a planning perspective, at least, we're going to be facing an extreme change in our generation portfolio as we're trying to, make progress towards our net zero goals. But we also need to understand that a lot of these challenges actually have already started presenting themselves, even though, perhaps on a smaller or more limited scale. And that's because the Dominion Energy, already has a very significant IBR portfolio, mainly again PV solar. Um, in fact, actually, we have the second largest utility-owned solar fleet in the U.S., where we have currently more than 3 gigawatts of renewables in our territory between Virginia and North Carolina. And so from this map, you can see all of the location of the transmission connected sites, which you can see are mostly found, at least so far, in the eastern part, and then particularly around the border between Virginia and North Carolina. In addition to that, though, we also have another 5 gigawatts of solar, which is currently under active development. And so that will bring our total to over 9 gigawatts in the very near future. Next. Now, another big component of our current renewable portfolio is what we call the Coastal Virginia Offshore Wind Project, or CVOW. And this is a 2.6 gigawatt offshore wind farm, which will be located off the coast of Virginia Beach. This is currently the largest offshore wind project in North America, and it's currently under construction, on schedule, and on budget, and we expect an in-service date of early 2026. And so, well, this is obviously a tremendous step forward for us, for our renewable portfolio. From a transmission perspective, coordinating the connection of such a large generation facility into our existing system is obviously a significant challenge. And so, for example, for CVOW, which is located 27 miles from the coast, and so because of that, as well as other reasons, but it was chosen to use a high voltage AC connection to shore and not HVDC. And so obviously this required significant transmission upgrades, especially in terms of reactive power compensation, which will be required in order for the wind farm to meet all of its voltage control requirements at the POI, the point of interconnection. And so these are example of some of the things that, just like Rahul was talking about, that need to be taken into consideration when thinking about integrating IBRs into the existing grid. Just like he said, it often requires communication as well as coordination between separate entities to make it all come together, and also to then reap all the benefits that we usually associate with IBRs, in particular if that's grid forming. Next. So again, based on where we stand, I will now try to discuss a couple of the more specific and more technical challenges that we already started facing from an operations point of view. One example would be issues related to system protections, which we've already actually started observing. Obviously at this point, basically all of the IBRs in our system are still grid following. And so that comes with limitations in terms of fault contribution and fault response. Things like limited fault current compared to traditional generation, but also, most of the times either no negative or very little negative and zero sequence currents, which then cause issues and misoperations of our protections. And so, for example, in this slide, in the diagram that you see at the bottom, we had a radial line with two transmission connected solar sites along the line. And we've observed that when a fault happened, we, on the grid side, the relays operated correctly. There was no issues there, and sent the trip signal to the breakers. But on the other side, the protections did not operate to clear the fault, and that was based on the fact that, like we've seen, we did a very thorough analysis of both the data that we got from our relays and digital fault recorders, but also then we performed hardware in the loop simulations. And we found that the issue, again, was due to the directionality element not picking up in this case because of the almost zero negative sequence component, which is what we use for determining directionality. Next. So then this is another class of issues that we've already started seeing, and that will be unwanted dynamics on the system, which are generated by some of our IBR sites and have the potential to spread across the system and possibly impact either other generation or even our customers. A lot of these things are directly related to the control schemes employed either at the inverter level or in the power plant controller, or even interactions of these two. And so the detection of these issues often starts from our system operators, which see issues, localized voltage or power oscillations, which are different from what they're used to see from our traditional system. And so what they do is they notify other groups within our electric transmission group, asking for our help, I guess, in terms of providing insight into what is happening and how they can react to it. And so on this slide, I have two examples of voltage oscillations that were caused by IBRs. And even before I get into that, I will say that, while for some of these we've been able to kind of track down the cause of the issue, there are still some phenomena that we don't quite fully understand, and we don't really understand the cause. But anyway, so in the plot on the right, so that's an oscillation that, as you can see, can be observed both in the voltage and in the reactive power signals, but not in the active power. And based on our analysis and what we found was that in this specific case, we had a badly set up control system, which introduced a significant communication delay in the AVR, in the automatic voltage regulator, and so caused the plant to start hunting and causing these voltage oscillations. So that was something that we were able to track down, understand, and it got fixed. On the other hand, the other example in the bottom left, that's a somewhat weirder phenomena that we've been observing, where we have oscillations that are actually continuously changing in frequency. So you can see them slowing down and speeding up. And again, this is something that we're not exactly sure where it's coming from. Next. So in any case, all of these challenges, all of these new behaviors that we're observing are kind of forcing us to develop new tools, new strategies to try and understand them and address them. Especially considering that while for now, they're somewhat localized or limited in magnitude, as IBRs are going to replace more and more of our traditional generation, we expect these issues to grow in severity. And so we want to be proactive and first understand them from an operational perspective, and then subsequently we will try to kind of engineer our system planning, our technical requirements to try and prevent them from happening in the future. And so in regards to the first part, one of the things that we are doing is to leverage our extensive network of measurements, both PMU but also point of wave data, to develop analytics for the identification of these dynamics. And so we're using tools like spectrograms, like we can see one here, which is a way to visually represent the power of a signal over time. And it allows us to track and even sometimes catch these behaviors before they turn into more severe events. And so actually this example that you see here on the left is a spectrogram corresponding to that fast and slow, the speeding up and speeding down oscillation that I just showed in the previous slide. And so if you look at the red trace, that's the highest power signal. And for a normal oscillation, we would expect to see a straight line, meaning a constant frequency. But in this case, we can see moving up and down as the oscillations speed up and slow down. On the right we have another example of another technique called mode shape analysis, which then allows us to identify the source of an oscillation by tracking the signal strength across the network. Next. And so all of these techniques and more are allowing us to detect all of these unwanted behaviors that we are seeing from our IBRs, but to really fully understand the cause of these and to also make sure that that we put in solutions to mitigate them. We are also doing a lot of modeling and simulation. And that will be especially in terms of using electromagnetic transients or EMT type of modeling, which allows for the detailed modeling of all of the components within an IBR site, and especially all of the controls that are involved, since we always try to use black box models that we get from our OEMs that incorporate the actual hardware control code. And so, while EMT simulations, as in the industry as a whole, we are kind of seen as the next step in both planning and operation studies, there are still many obstacles that are slowing down the adoption. And so in our specific case, one of the main challenges that we have is the fact that we are not currently requiring new IBRs that connect to our system to provide EMT models of the plants. Right now, it's still just positive sequence PSSE models like Rahul mentioned. And so when we need to perform these EMT studies to try and address whatever issues we might have observed, we actually have to go back and somehow try to pull together all of the information, all of the data to be able to build these models. But that's obviously, it's not an optimal process. And many times this has hindered our ability to actually successfully perform these studies. And so what we're doing is we are currently working internally to define our own modeling and validation requirements that will then be included in our facility interconnection requirements, which is what anyone that's connecting to our system is required to adhere to. And we know that eventually NERC and then PJM, they will start mandating this in the future. But we're trying to be proactive since we can't really wait on them anymore for this. Next. Another thing that we've really put a lot of emphasis on at Dominion is real-time EMT studies and hardware in the loop studies. We actually got started with this about over a decade ago, when we first began to adopt fax technology, especially STATCOMs. And we saw a great value in being able to perform all kinds of studies in the real-time environment, where we can interact and interface with physical controller replicas of these devices. And so we are now at a point where we have a pretty substantial state-of-the-art RTDS lab, which we use for all kinds of studies, including protection and control studies related to IBRs. And again, because of this experience that I was talking about in terms of with using FACS replicas, which it really helped us gain a much better, much deeper understanding of this technology. Now we want to do something similar for IBRs, and so we're actually in the process of acquiring both physical as well as software replicas of some of the main inverters that we have on our system, to obviously improve our simulation capabilities when there's issues, but also just improving in general our understanding of the controls and also how these devices kind of behave once we connect them in a real power system. Next. And so all of these things, these are very detailed, somewhat localized studies that allow us to identify or even correct issues related to specific IBR sites. But we also need to be thinking about like the higher, like the system, from a system-wide perspective, to try and really understand the impact that such a large growth in IBRs will have on the way we both plan and operate our system. And so that's where our group is also performing studies that look at what would be traditionally more like a planning type time horizon, but that, at least for now, fall outside of the traditional processes that PJM follows and that Rahul described. And so, for example, we've been looking at things like how the short circuit current or the short circuit strength and inertia of our system will evolve in the future as we integrate more IBRs. And so we've looked at 5 and 10 years ahead using the planning cases, which integrate all of the expected IBRs based on the PJM queued. And we found that overall, at least for now, our system is expected to remain pretty strong, and reliability won't really be impacted outside of just smaller or more localized issues. So that we saw actually that obviously in location where there's going to be a higher concentration of IBRs, the short circuit strength will be decreasing. On the other end, though, because that's not the only changes that are happening to the system. At the same time, we're always constantly upgrading our transmission system and creating new lines and upgrading our lines. We actually saw areas where the short circuit strength will actually increase. And so overall, on a net, like this was a kind of a, again, the reliability will stay pretty constant and within good levels. Something else that we're also now doing is to look at the short circuit ratio, and we use different short circuit ratio metrics pre and post events to try and understand if any of the changes that might have happened in the network based on outages or forced outages or whatnot, if those created low short circuit ratios that then gave rise to some of the oscillations, some of the issues that we've observed. Next. And then finally, one other major aspect of our, I guess we call it like of our IBR strategy, which really believe is critical for us, but also for the industry as a whole, is just fostering relationships and collaborating with research labs and academia. And so, for example, we really, really appreciate opportunities like this today, where you have people that are leading and pushing for the development and adoption of new technologies, giving us, a utility, a platform to share our perspective, as well as some of the specific challenges and opportunities that we see. So in addition to that, we obviously also have, we try to maintain strong relationships with several universities by directly collaborating on research projects that we believe might help us in the future. And so I have a couple of examples here. We recently just got awarded a DOE grant to collaborate with Virginia Tech and Mitsubishi Electric to develop new or improved grid forming controls with a focus on solving many of the limitations when it comes to protections, so that it would allow us to integrate new grid forming technology more easily within our existing protection systems. Another example is a project, again, with the CPES lab at Virginia Tech, that's looking at the use of IBRs for system restoration. And so there we are looking at both, what role can the current technology play in supporting the restoration process, but also looking further in the future, we're looking at developing new control schemes to make it possible for an IBR to act as the primary black star resource. And with that, I will pass it back to Rahul to go over one last example of a collaboration that we have with a university, and then to close the presentation. So thank you all.
Thanks, Andrea. So with that, I want to show you all briefly the collaboration we have with NC State. So I was personally involved with my alma mater, NC State, in Freedom System Center to kind of help in one of the PhD student CHN's dissertation in one of the work she's working on. So what I bring in this work is like the utility perspective when it comes to studying the grid forming control technologies. Most of the experiments which are done are typically in the sense of single machine infinite bus kind of scenarios, and fault right through scenarios like voltage sag with fixed infinite bus frequency or frequency sweep without voltage magnitude change does not actually faithfully represent the AC network transient. So our strategy was to kind of test the solution in a network of inverters. And as you all know, IEEE 9 bus is like one of the very simple transmission level model where we replace the generations with GFM, kind of use the GFM controller architecture, where with the standard virtual admittance based current reference generation, the circular limiter, and all the standard stuff. We saw that, okay, with the constrained enforcement, how that impedes the transient stability. And when it comes to like power limiting in response to frequency events, the current limiting in response to the under voltage or AC grid faults, how we can improve the response of the resource, grid forming resource. So we kind of came up with this power reference adaptation based on terminal voltage and the P omega droop dynamics compensation to see how that enhances the performance. This was recently presented in the ECC in Phoenix. The overview of the result, it's like a motivational example where it shows that, okay, if we have no capacity constraint, then the phase portrait, it looks like this. Whereas if we have a capacity constraint, that deteriorates the transient stability, causing angle acceleration during fault and after fault clearance as the limit enforcement takes place for the IBR, which was operating at its limit, that demands power output that cannot be achieved by the capacity constrained grid forming control. So the power angle of that IBR continues to accelerate compared to the other two IBRs in the network. This basically deteriorates the transient stability. And after fault clearance, it causes the post contingency operating point to reach like a completely different location here. Whereas with this adaptation in the control loop, we show that, okay, we can bring down the phase portrait to a more stable performance, and we see that it's achievable. But this is a more simplistic example. Like I mentioned, here we also evaluate the conservative transient stability index, which shows the delta max is basically the maximum angle deviation between any two IBRs. And here we show that we can improve with our control strategy, we can improve the transient stability index. But here we have used different simplistic assumptions, right? Because this study here, we assume the loads are constant impedance load. Here we have simulated contingency, which is like three-phase to ground fault. But when it comes to real utility operation, the load can not only be like constant power, constant voltage, constant current, constant impedance, but it can be a combination of that, or it can be a totally different type of animal like data centers, where the power oscillations don't typically follow the regular pattern. Like a AI training data center can have a very different pattern than a data center which is kind of giving web services. So those type of complication will require us to do better load model. And also this new emerging large loads like data centers or crypto mining facilities, they are inverter interface load. So why I mentioned this here, because UNIFI is developing the standards of operation for inverter interface resource. We also need standard for inverter interface load like data centers, so that we can host them with like maintaining our reliability of the transmission grid. So these are like some of the external collaboration, and then the key takeaways from this presentation is handling the future load generation scenario need like a multi-solution planning approach. We need reforms in the interconnection. We also need the more non-wear investment. Like if we just propose new lines to connect the generation with the load center and build a big interregional transmission line that do enforce the reliability, but we also should think that those implementation of the projects take years, and with the supply chain issue, the timeline is even increasing. So that's why we need more like a non-wire investment. We need dynamic line rating support, we need energy storage, we need virtual power plant from distribution. So all this Dominion is working on, and we have like a multi-solution approach. The GFM GFL requirement should come from the ISO, and that is going to change how the multi-regional electricity market works, coming with all these ancillary services, even from offshore wind. If we have all the offshore wind in the east coast in the different utility, building that, and we can connect them through HVDC that the DOE has released a report on, then there will be a huge change in how the electricity market even works. So all these change are going to take place, and these type of reforms are the need for the GFM, grid forming technology, to come predominantly in the future. And performance requirements of IBR need to be more stringent and specific than they have been so far. Like detailed studies are required to define these requirements. IBR performance must be evaluated and analyzed from like a systems perspective, not only like each IBR in like individually. So yeah, that's our presentation, and we are open for question and answer. Thank you.